Thought about it.
Yeah,
I feel like it's
yeah.
a lot of aspects, but not rejected, which I feel like talking to other people, they were like,
It sounds fun.
Yeah, right, yeah. Well, I feel like it's a pretty well-read paper, so maybe if you get it published, yeah, start getting citations.
It's on the menu.
I was really excited.
oh, I got DP. Yeah, it was like,
Yeah, another fight.
it was.
Hello, everyone. Let's get started. Okay, thank you, everyone, for joining today's CGD seminar. I'm Jiang Zhu, host for today's seminar. The title of today's seminar is The Green Sahara as a Driver of Holocene Climate Dynamics. This seminar is also part of the CSM Paleoclimate Working Group meeting. Our speaker is Victoria Todd. She's with us online. And Victoria is a PhD candidate at the University of Texas at Austin and incoming ASP postdoc fellow at NCA. So she will be joining us soon. And she's a paleoclimatologist whose work integrates geochronology, organic geochemistry, and Earth system models to investigate the physical mechanisms that govern hydroclimate variability across past, present, and future climates. During the seminar, please hold your questions until the Q&A session at the end of the talk. And for those who are watching on YouTube, you can submit your questions via Slido. So go to slido.com and use the code CGD seminar. With that, Tori, please get started.
Okay, great. Thank you so much for the introduction, and thank you so much for having me. So just to start things off, I would like to briefly thank all of my collaborators for your years of advice and your hard work on many of these projects. So today, I'm going to talk about how the Green Sahara acts as a major driver of Holocene climate dynamics and why it provides one of the best natural experiments for testing land-atmosphere feedbacks in climate models. So just to walk you through what we're going to be talking about today in this talk, I'll focus on two case studies that showcase the importance of land surface feedbacks during the Holocene. How this ties in work at NCAR. To give you a brief introduction, first we start off with the big question and the big problem. And that is that while climate models are in good agreement about future temperature changes in regional precipitation are very uncertain, with the CMIP models showing a large spread in the possibilities. You can see that here in these figures, where the stippling indicates regions of low CMIP6 multi-model agreement. This, of course, has huge implications whenever you're thinking about how we can do risk management and how we can understand how resources are managed into the future. So how can we reduce the uncertainty in these projections? So while the observational period is only around 150 and 200 years long that we can use to compare to CMIP, we can use paleoclimate to provide additional out-of-sample tests for these models. And one of these paleoclimate periods that is often part of one of these paleoclimate intercomparison modeling studies is the mid-Holocene. As you can see from this chart, this is a relatively warm interglacial period, not unlike what we see during the last interglacial or in the recent past. So during the mid-Holocene, greenhouse gases were near pre-industrial levels, and ice sheets and the continental configuration was pre-industrial as well. So what's driving these changes during the mid-Holocene is this change in insolation forcing. In the Northern Hemisphere, coming out of the LGM, you have a large increase in Northern Hemisphere summer insolation forcing. And conversely, in the Southern Hemisphere, you have a decrease in summer insolation forcing. So while you would think that these changes that we see during the mid-Holocene are pretty small in comparison to those that you see during deglaciation, actually, many proxy records all over the world document large mid-Holocene climate changes. And many of these records suggest that mid-Holocene temperatures may have been warmer than what we see during pre-industrial. So to give you a really visual example of this, we see 6K vegetation that underlies glacial ice. And then more quantitative temperature compositing efforts also see this same mid-Holocene warmth. What happens when we simulate this period with climate models? As we can see in this top curve, while proxy reconstructions for the Holocene generally show this early to mid Holocene warmth, followed by cooling towards the pre industrial, when we simulate this period with climate models, what we generally see is cool early to mid Holocene conditions and a gradual warming towards present. So in this way, the proxy reconstructions and the model simulations appear to be in disagreement. And this disagreement between what the proxies have reconstructed and what the models are showing us is what's known as the Holocene temperature conundrum. So while summer Northern Hemisphere insolation was increasing, this also drove a strengthening of Northern Hemisphere monsoon systems, which includes the West African Monsoon system. And the strengthening of this monsoon system is recorded in many different proxy types from this region. So we see the expansion of these large mega lake systems and river systems. And we also see the expansion and this change in vegetation types in the Sahel and the Sahara. So we're replacing what is currently desert regions with these woody grasslands and woodlands and expanded forest cover. And this is what's termed the Green Sahara. So what happens when we try to simulate these changes that we see in Northern Africa? So in this chart, you can see changes in mean annual precipitation in Northern Africa. This is by latitude. And this is in several different PMIP2 and PMIP3 models. And what we want to compare these changes to is the changes that we see in the proxy record, which is indicated by the data column on the right. So what we can see is that the PMIP2 and PMIP3 models are really underestimating the precipitation changes we know from the proxy record occurred in Northern Africa. So it's important to note here that this is even occurring in these PMIP3 simulations, PMIP2 and PMIP3 simulations with fully coupled dynamic vegetation modules. So if we want to understand these regional changes in hydroclimate over Africa during the mid-Holocene, we need to use simulations with prescribed mid-Holocene vegetation. What we find in these prescribed vegetation simulations is that as you're replacing this light, bright, and reflective desert surface with this dark vegetated one, you're driving heating of Northern Africa. And that this heating is driving a stronger Saharan heat low, and that this increases precipitation in the Sahel and the Sahara. We can see this that in these simulations with prescribed vegetation in this region, the mean annual precipitation that we're receiving in Northern Africa is now much closer to what the proxy data suggest. But in these simulations with prescribed vegetation, we do see changes elsewhere in the climate system. So first, just to walk you through this, this is the CESM simulations with prescribed vegetation, or excuse me, with pre-industrial vegetation. And as you can see, these are in agreement with other simulations of the Holocene. So they really are in agreement with previous simulations. But what happens is that as we add increasing vegetation cover on Earth's surface to the Northern Hemisphere, we start to warm the Northern Hemisphere in such a way that these model simulations are now in agreement with what we see in the proxy record. So they're really close to what we're seeing in the proxy record. So in this way, this prescribed vegetation cover is one potential solution to the Holocene temperature conundrum. So now that we've set the stage there, I'll briefly tell you what I do. So what I do is I use climate models and proxy data together so we can better understand the climate system response and how models are simulating this behavior. So I do this in a variety of different methods, including geochronology, and then also doing sediment geochemistry. So let me walk you through those methods very briefly now. Oh, okay, so in these case studies, we are reconstructing changes in climate using biomarker-based approaches. So we can have quantitative numbers basically to compare to these climate model simulations. So the first of these biomarker-based approaches is measuring the stable isotopic composition of sedimentary leaf wax molecules. And these are these long chain carbon molecules that are biomarkers for terrestrial plants. And these leaf waxes are preserving the isotopic signature of this paleo precipitation. Then the second biomarker-based approach that I use in these case studies is reconstructing paleo temperatures using the MBT prime 5 ME index. This is based on changes in the degree of methylation in bacterially derived branched GGTs. So as you can see on this right-hand chart, these structural variations, which are quantified by the MBT prime 5 ME index, are empirically correlated with temperature. And in this way, we can reconstruct paleo temperatures from these lake core sediments. All right, so that brings us to our first case study. So this work is, that I'll be showing you today is from a recent paper that we published in Nature Geoscience in July. Just to set the stage for climate in the Southwest US, the Southwest US is a very drought-prone region today. So in 2020 to 2021, these conditions were the most severe droughts in the past 900 years. So the area had been under what was termed a mega drought since around the year 2000. So this has severe consequences for the Colorado River system. What's also really important to note here is that winter precipitation declines are extremely devastating for this Colorado River basin, as it relies on winter snowpack to sustain water flow and water resources throughout the year. But of course, persistent drought in the West is not new. And one potential analog can be the mid-Holocene. Previous studies had shown widespread drought in this region, though quantitative estimates of this drought are scarce. And even less is known about changes in precipitation directly, as it's very difficult to separate changes in precipitation and changes in evaporation. So that we could better understand hydroclimate changes during the Holocene in this region, in our lab group, we reconstructed several new hydrogen isotope records from lake sediments in the Southern Rockies. You can see this transect that we've done here. I'll also note the location of Leviathan Cave, which is located in Nevada. So here on this left chart, you can see some of these leaf wax delta D reconstructions from Stewart Bog, Hunter's Lake, and Kite Lake across the southern Rockies transect. And what you'll see in all these records is that they're very coherent and suggest that there's this coherent, insolation driven, large scale change across the southern Rockies. So additionally at the top, I plotted the Speleothem Delta Utino record from Leviathan Cave for comparison, which we just saw was located actually pretty far spatially away in Nevada. And together, the overall agreement between these records really do suggest a large scale change in hydroclimate in the Southwest US during the Holocene. So all of these records are showing a shift to really positive isotopic conditions during the early to mid Holocene. And it's really this signal that I want to be focused in on in this talk. So it's important to note that in this region, nitrogen isotopic composition of precipitation is very seasonal. So winter precipitation sources are very northerly and have a very negative isotopic composition, while summer precipitation stable isotopes are quite positive and derived from these southerly and southwesterly moisture sources. So whenever we're trying to think of how we will interpret these new leaf wax delta D records, we know that these leaf waxes are going to be reflecting some mixture of these changes in winter and summer precipitation. So whenever we're thinking about this more positive isotopic anomaly, we could either be seeing a reduction in winter precipitation sources or an increase in summer precipitation sources. Either one of those could be driving this change that we see in our records. So in order to quantify the possible changes in winter and summer precipitation that would explain the isotope signal that we see in these records, we developed this Bayesian stable isotope mixing model approach with these two end members using the modern distributions of precipitation isotopes for this site. We calculated the possible proportions of winter and summer precipitation that would explain the signal that we see in our proxy records. We also added the constraint that precipitation during the mid-Holocene was less than the precipitation that we see modern. And as a result, we have this plot of the possible changes in winter and summer precipitation that would explain the isotope signal that we see in our records. So here you can see the result of that Bayesian stable isotope mixture modeling from Stewart Bog here in this right here. On the x-axis, we have the change in winter precipitation in percent. And on the y-axis, you have the change in summer precipitation in percent. And to benchmark these changes against what we see in climate models, each one of these plus signs represents a different PMIP3 model for this region. And what we saw is that all of these models were underestimating the winter precipitation changes by around 15 to 20%, which was pretty substantial. And we were trying to figure out exactly why that might be. So as I discussed earlier, these models are showing a cold early Holocene, which may not be in agreement with what we see in proxy records. So for that reason, in this study, we used a multi-model ensemble of simulations with prescribed mid-Holocene vegetation. I'd like to thank my collaborators for their contributions there. So what we find in this ensemble of prescribed vegetation simulations is that with increasing prescribed vegetation, so going from pre-industrial vegetation to Green Sahara, to these mid-latitude and northerly prescribed vegetation, what we find is that with increasing vegetation, we always see this increase in northern hemisphere temperatures. And in addition, we also see a decline in winter precipitation in the Southwest US. But this northern hemisphere warming that we see with increasing vegetation cover is not uniform. So it results in this distinct lobe of warmer sea surface temperatures that extend from west to east across the North Pacific, and this region of cooler or unchanged temperatures along the coast of North America. I'll also note here that we see a similar pattern in EC Earth with no vegetation change, which suggests that this pattern may be arising due to something to do with the northern hemisphere warming and not necessarily to do with vegetation. So what's interesting about this pattern is that this change resembles what we see during the negative phase of the Pacific decadal oscillation in the modern. And this configuration of SSTs is known to drive drought in the Southwest US. So next, we wanted to know if the proxy data of sea surface SST proxy data in the North Pacific agreed with what we saw in the PMIP ensemble, or if it agreed with what we saw in this prescribed Holocene vegetation ensemble. So we synthesized many SST records from this region, and while the SST data is pretty sparse, we generally see this warming in the Kuroshio Current region of Japan, and we generally see cooling along the coast of North America, which was more consistent with the changes that we saw in the simulations with prescribed vegetation. Oh my gosh. Okay. Oh, oops. Okay. So next, we synthesized hydroclimate records from North America. And what we find in these proxy records is generally we see this dry, wet, dry pattern of proxy precipitation changes. And these were in closer agreement with what we saw in the Holocene ensemble with prescribed vegetation. It's also important to note that this is the same pattern of precipitation changes that we see during the modern negative phase of the Pacific decadal oscillation. So next, we wanted to figure out exactly what was happening in this CESM simulation with prescribed mid-Holocene vegetation. So we used output from that run to conduct some sensitivity experiments. And what we find is that with just this greening of the Sahara, so with no sea surface temperature changes, this already drives this northern hemisphere warming over the continents and this weakening of the Aleutian low. So we hypothesize that this may initiate this sea surface temperature pattern that we see in the models. So this really got us thinking, what about future climate? So if we think that this is somehow emerging due to northern hemisphere warming, in ongoing anthropogenic warming, what we're seeing is a large warming of the northern hemisphere. So we put together many large ensembles of climate model simulations from the historical and projected periods, and actually out to 2100. And what we see in these detrended large ensembles is a shift to a negative PDO index out to 2050 and out to 2100, actually. And it appears to continue as long as Northern Hemisphere warming continues. So this is important because it suggests that this pattern might continue emerging. And we know that it drives drought in the Southwest. But back to this plot. So even in these simulations that get this sea surface temperature pattern and do drive some drying in the Southwest, the magnitude of the mid-Holocene drought was still underestimated. So we wanted to see if this is a common response to this PDO-like pattern in the North Pacific. So we looked at observations of the negative phase of the PDO. And you can see that there on the left. In these observations, we see this much larger precipitation change than we do in simulations. So this would suggest models are likely not, they're likely underestimating these winter precipitation changes in the historical and in the Holocene. And this is likely to continue into the future as well, even if we are getting this sea surface temperature pattern correct. This has several implications. The first of which is that future warming may lock us into this permanent negative PDO-like configuration of SSTs that we know is associated with drought in the Southwest US. And that also models may be underestimating these impacts on winter precipitation and as a result, future drought risk as well. All right, so that brings us into our second case study. So this is part of a paper that we just submitted to Nature Geoscience. This is a photograph I really like from an astronaut showing the Lake Titicaca that I'll be discussing in some detail. So this Holocene record that we'll be discussing from the high Andes is part of a much longer record that I've been working on in the past few years from Lake Titicaca. So utilizing the 2001 drill cores from this site, we've done a lot more geochronological work on these sedimentary drill cores, and we've also done new biomarker-based reconstructions. And together, we now have long records of temperature changes and of precipitation isotope changes from this site extending back for the last 350,000 years. And this can give us a lot of really great information about how this site responds to interglacial warming. And this may inform how we think about how the site is currently changing today and how it may change into the future. But in order for us to understand the changes that we're seeing in this much longer record, it's important to first break down these changes that we're seeing during the Holocene. So here you can see this Holocene record from Lake Titicaca. And then additionally in this study, I did another nearby record, Laguna Yanacocha. You can see that overall the Delta D records from both of these sites are very similar. They all show this positive isotopic anomalies starting at, around 10 to 9 Ka, and then with gradual shift to more negative isotopic position towards the pre-industrial. They also both show this millennial signal centered around 2 Ka. That's definitely going to be the future study. So what's really important about these sites is that they're located in the central Andes, which is really central to the South American monsoon and is kind of at the southern extent of this monsoon system. So they're really giving us an expanded kind of transect of records across the Andes. So when we usually think about Holocene changes in the Andes, we're usually thinking about records like these that show this coherent insolation-driven change with the lowest for insolation in the southern hemisphere corresponding to the most positive isotope values during the early Holocene. And then as insolation starts to increase, we start to see more positive isotopic anomalies, which would be interpreted as wetter conditions. So in this way, how we usually think about this is that these change in the South American monsoon system is largely driven by local insolation. And we would interpret our much longer record as reflecting local insolation changes. But what I really wanted to ask in this study is local insolation the whole story? So here you can see our records put together with the rest of this transect. You can see that overall, these records are all fairly similar. You have this shift to a Holocene maxima that's centered at around 9 or 10 Ka, gradual decline towards the present. But what's really interesting about this Holocene transect is that you get larger isotopic anomalies during the mid-Holocene towards the south, so towards the southern extent of this Andean transect. So this transect has basically this isotope gradient of anomalies during the Holocene. But because we have so many great isotope records from this region for the Holocene, we want to be able to compare the isotope changes that we see in our proxy records directly with the precipitation isotope changes that we see in the climate models. And to do this, we use the CESM 1.2 isotope-enabled Holocene time slice experiments. What we find is that in this experiment forced with insolation only at 6 Ka, that the precipitation changes in amount, but the precipitation isotope changes are pretty small in this model. So when we look at this more quantitatively in the scatter plot, where we're looking at changes in proxy delta 18O on the x-axis and changes in modeled delta 18O on the y-axis, what we see is that at 3 Ka, where the changes are very small in the proxies and in the models, we're in pretty good agreement here. But then at 6 Ka, the proxy delta 18O changes are quite a bit larger than the changes that we see in the model. Next, we wanted to see what was happening in these simulations with prescribed vegetation for 6 Ka. And what we see is that there are much larger precipitation changes in the South American monsoon region. And we also see this reflected in the precipitation stable isotope runs in this study. When we look at this again in the scatter plot, while the modest vegetation changes at 3 Ka really don't make much of a difference to the signal that we're seeing, 6 Ka, this actually makes a substantial difference. And it brings these delta 18O and model delta 18O values into alignment. So you can see that one-to-one line here. So next we wanted to figure out exactly why that was. What component of the Green Sahara was causing this? And in order to do this, we first wanted to look at these changes more seasonally or monthly. So on this x-axis, you can see this broken down by month, and we're looking at changes in delta 18O and changes in precipitation for the central Andes region over land only. And this is broken down by latitude. So what we find is that in all of these simulations, 6K PMIP and 6K Green Sahara, and 9K as well, these changes are really focused on what's happening in the shoulder seasons. And especially in the Green Sahara runs, we get very large changes in delta 18O and in precipitation as well, focused on March and April. So really when you get this withdrawal of the South American monsoon atmospheric circulation, when that's beginning to weaken. So next, we wanted to figure out exactly why that would be. There's a lot of changes going on in the climate system in these Green Sahara runs, as we just saw in the talk previous to this one. And so we broke this down once again by looking at these sensitivity experiments that are isolating the different components of this fully coupled run. So this includes global SSTs, tropical Pacific SSTs, and vegetation only, so with none of these SST effects included. So you can see that in the global SST and tropical Pacific SST simulations, that the changes, especially in the central Andes region, are pretty minor. We can also see this when we break this out by month. This really doesn't incorporate those shoulder season changes that we know is so important for the isotope signal. However, when we look at the vegetation only simulation, what we find is that this better explains the drying that we see in the central Andes, not only when we look at this spatially, but also when we look at this month by month. We're trying to figure out what about this vegetation change would drive significant changes in the shoulder seasons. And the answer to that is that in this left-hand portion of the figure, you can see that with this change in prescribed vegetation, you are driving a lot of warming of Northern Africa. And this is essentially asymmetrical tropical heating. So what you see in a typical Gill's model. And this effect appears to be strongest in the shoulder seasons whenever this monsoon circulation is weakening. What's happening is that this is driving a change, a zonal change in moisture flux convergence with divergence over South America and increased convergence over Africa that is dynamically driven. So this has several implications. And the first is that American drying in the early to mid Holocene isn't explained by just local insolation changes alone. This is important when we think about how we're going to interpret this much longer record. We also find that land surface changes dominated tropical hydroclimate responses in the past, and that for that reason, it stands to reason that predicting future Andean hydroclimate may lie in getting land surface feedbacks right in climate models. So all of this ties into my future work here at NCAR, which is how do we simulate a green Sahara? So as we talked about in the introduction, even when climate models are run with fully coupled dynamic vegetation modules, we still are not reproducing green Sahara conditions. And this suggests that either the atmospheric model or the land model or the coupled interactions between the two are not responding strongly enough to this mid-Holocene change. So the first question I want to ask are are the dynamic vegetation models the problem? So is this the limiting factor? So in a study from Hopcroft et al. 2017, he benchmarked several different dynamic vegetation models against what we see in observations here on this left-hand side. On the x-axis of these charts, you can see precipitation in millimeters per year, and you can see grass coverage on the y-axis between 0 to 100%. And what we really want to look at for understanding the Green Sahara is where does this transition from bare soil to grass coverage occur? So what we see in LPJ and Joules, two of these dynamic vegetation models, is that they require much more precipitation in order to make this transition from bare soil to grass coverage than is suggested to be realistic from observations. However, when we take a look at SDGVM, this model actually pretty reasonably approximates what we see in observations. And if anything, SDGVM shows too much vegetation coverage in arid regions. So you would expect that a dynamic vegetation model like this one would actually be a little bit too eager to green the Sahara than the actual climate system. So what happens when we run SDGVM with humid precipitation? So what we find is that in order for the vegetation simulated by SDGVM to approximate what we see in the proxy record over here, we actually need mid-Holocene PMIP precipitation to be multiplied by 3 and shifted northward 10 degrees. So this suggests a substantial change in precipitation and suggests that we should probably be taking a closer look at the atmospheric model. So this is modified from a figure produced by the Mesoclip group in a really great paper that was published in, I think, November of last year. And first, I want to just show you this left-hand column of observations. Observations are showing us that these large precipitation events that we see in the Sahel are generated by mesoscale convective systems, which are represented by this red color here. And these MCSs are key for the propagation of storms into the interior of the continent. When we look at the difference in atmospheric phenomena that are seen in the high versus the low resolution configuration of the CESM 1.3, we find that while the low resolution model does not produce these MCSs in this region, high resolution configuration does produce MCS-like phenomena in this region. So it's important to note here that this low resolution configuration of CESM 1.3 is actually higher resolution than most CMIP and PMIP ensemble members. I would suggest that MCSs were likely crucial to producing the wetter conditions of the mid-Holocene, and that these data would suggest that the ability to produce these systems and these atmospheric phenomena is resolution dependent. So thinking about things that way, now if we look at simulations using this high resolution CESM 1.3 configuration, we can see these changes in precipitation. These are showing anomalies between mid-Holocene and pre-industrial in the low resolution and the high resolution. So the only thing that's changed between these two configurations is the resolution scale at which they're run. And what we can see is that the high resolution model produces much larger rainfall anomalies, especially in this Sahara region. And it may be even more helpful if we look at this bottom plot, which is showing the high resolution minus the low resolution mid-Holocene precipitation anomalies. We can see that the high resolution model is producing much larger precipitation changes much further inland than we saw in the corresponding low resolution model. So I'm hypothesizing that this is due to the better process representation in the high resolution model. I'm very excited to explore that in more detail. So in conclusion, across these projects, I've shown that land surface feedbacks are very important for shaping regional hydroclimate responses. And the goal of my future work at NCAR is to use the Green Sahara as a benchmark for climate model performance to improve predictions of regional hydroclimate. Thank you.
Thank you, Victoria, for the great talk. Now we have time for questions. Dan.
Thanks for a really nice presentation. I was wondering if you had looked at any of the precipitation changes in South America in the higher resolution runs and seen any changes there that might not be from Green Sahara, but just from increasing resolution.
Yeah. So I have taken a little bit of a look at these runs, and they're actually pretty similar to what you see in the insolation only forced runs, but of course the precipitation extremes are much higher. But I really do look forward to exploring those in more detail.
Cool, thank you.
Just another reminder for people who are watching on YouTube, please submit your questions via Slido. So go to slido.com and use CGD seminar. Any more questions?
Yeah, thanks for the really nice talk. I had a clarification question maybe about your PDO plot. I was really surprised to see such a big ensemble mean signal. Were they normalized in a way that it's actually the ensemble mean is a much smaller signal than the observed PDO? Or do they actually represent the same signal in like SSTs and Kelvin?
Yeah, so they all represent the same amount of like real units.
Have more questions?
Yeah, I have a question.
Oh, yeah.
Yeah, thanks for a great talk. I have a general interest question about delta D and leaf wax. How do you
Great.
get error bars on it? I think one of your plots had kind of a shading around the different leaf wax records. I'm just curious how you come up with that.
Sure. So in terms of the horizontal error, that's coming from our age models, which it's always really important to try to improve age models and to make sure that the signals that we're seeing in our record are actually at the correct time. But in terms of the vertical error bars or that real uncertainty in the delta D wax measurements, that comes through replication. So each one of those points that you're seeing on that graph actually represents about 2 to 3 measurements of the same sample. So you really want to measure that over and over. And generally in our lab, at least, you get about, gosh, I don't want to like put too big of a, it's definitely less than like a 1.5 per mil application error in delta D.
Yeah, great talk, Victoria. I had one question also about the PDO section of your analysis, where you were showing, I think, this is kind of the question to like, what was the sea surface temperature pattern? Because you were linking warm temperatures in that Kuroshio, like Oyashio extension region to drought in the United States. But I might be wrong, but isn't it often like the cool temperatures in like kind of the equatorial Pacific and that La Nina-like state that's commonly associated with drought? Like, were there cooler conditions in the equatorial Pacific in your mid-Holocene experiments, or is it entirely just driven by this like warming?
Yeah, so we looked at that as well, because we were quite curious about that too. So in most of these simulations, you see, kind of as we've discussed in the last talk, kind of a more neutral state in the tropical Pacific, which is more La Nina-like. So we were thinking like, oh, maybe that is what's driving this drought. So in order to kind of understand that, we did some sensitivity experiments just to isolate, oh wait, I think I have that. Just to isolate how much of a contribution is coming from those tropical sea surface temperatures.
Oh, nice.
All right, I'm just gonna share this really quick. Window. Okay, so I put this in my bonus slides here. And what we find is that with these tropical Pacific SSTs, they are definitely contributing significantly towards the drought, but that this PDO is still a really substantial part of this drought response that we see in the Southwest.
Okay, cool. Yeah, thanks for the extra.
Yeah. Yeah, yeah.
More questions? Maybe I can ask one. I think one highlight of your talk is you stress the importance of land-atmosphere interaction, and you showed that the vegetation over Sahara plays a very important role. I'm wondering about maybe land surface change over the other regions, including during the Holocene. From proxy perspective, do we see big changes in the land surface cover, and should we expect a big influence from other land changes over other regions as well?
Yeah. I mean, I definitely think that those can be extremely significant. And we also see that whenever we compare, if you just have the Green Sahara region green versus that other mid latitude and high latitude greening during the Holocene, that this can also make a huge difference for global mean temperature as well. So while they're extremely important, sometimes we kind of abbreviate this, especially in our studies, to say Green Sahara, just because it is our most significant region in terms of spatial area and in terms of effect. Global climate changes is that greening of the Sahara.
Thanks.
Yeah, just a quick question. You showed comparisons using like 3 different or 4 different land surface or land models. And
Yes.
And I mean, given that these are dynamic vegetation responses, those differences could be simply associated with a bunch of if statements in those land models when they trigger certain things. Have you looked at those aspects rather than dealing with atmospheric forcing?
Yeah, so actually the authors of that study, Hopcroft, looked a lot at what the different thresholds were for vegetation growth in these 3 different dynamic vegetation models. And while there's definitely, significant differences between these models, and I also want to note that these 3 dynamic vegetation models that were benchmarked are pretty are of intermediate complexity and are nowhere near as advanced as, say, the current development of FATES. So while vegetation models have certainly improved over the years, some of these improvements have been implemented into the CMIP and PMIP models. So if we look at like some of the HAD-CM3 GEM type models, we still don't see, even with those improvements in the land surface model, we still aren't greening the Sahara in that region. So for that reason, I do think that it's probably time to look at the atmospheric model instead.
Thank you.
Yeah, thank you.
Following on that, I was wondering if, if you're thinking that some of these changes that you see are arising from large-scale atmospheric processes, does that suggest bringing to bear some of the proxies for those systems on the problem? Can you use, is there additional information out there that you could use to constrain it?
Oh, I'm sorry. Could you state that question just one more time? I think I'm having internet issues.
Oh yeah, absolutely. So if a driver is large-scale atmospheric patterns, do you think that there are additional proxies to the leaf waxes and other local things about the large-scale atmospheric circulation that could be used to constrain and support hypotheses?
Oh, absolutely. Absolutely. And that's really what I try to aim for in these studies. And what I will try to continue to do in my future work is trying to find agreement and convergence from multiple different types of proxies and multiple different lines of information. So thinking about things like land surface temperatures and how that plays a role into things too is always kind of at the forefront of my mind as well.
Do you have any more questions? Also no questions online. So thank you everyone for joining the CGD seminar. Let's thank Victoria again. And for people who are interested in talking to paleo folks, we have a reserved table in the cafeteria, so join us for lunch. And for people who are going to the working group meeting in the afternoon, it will start at 1 p.m. in the Damon room. Thank you, everyone.
Thank you. Bye.
Oh my God.